Also, like this year, I'm going to one more.
Morning, folks. Hey, how's it going? Good to see you guys. Excuse me. Can you look at? It's a tough problem. I don't know what we're doing wrong. We're gonna have to try
Actually, it's paper, all these interior binding conditions and the exterior things, it's working, and I also don't see exactly what's working.
I think what we do is where the sheet is displaced from the dielectric cube. It's a good way to at least verify that we have all things for the previous curves. When we write all three of these equations. I think that's a good idea. All right, let's
Virginia, it's like close to here.
Ridiculous.
Yeah. Little bit. I've worked on a couple projects where like not at all on my major. Where the civil engineers that do like structures and buildings, they have this big one too, where they'll like explosion. Yeah. Yeah, they want to see.
For those of you online, I'm not sure if you can hear me, but I have the meeting chat open. If you have any questions, they should pop up here and I'll be able to see them. And I believe you might be able to unmute yourself and talk, so you can interrupt me at any time, just to let you know. All right, it's 9:30, so let's go ahead and get started, guys. All right, so here we are, lecture 2 of electromagnetic fields or electromagnetic waves, ECE 5105. We're going to first recap one thing that I promised that I would get to you guys last lecture, and that is the concept of integrating a vector field over some contour in space, right? You do that a lot when we do the when we defined what the curl of a vector field was. We ended up expressing it in terms of a line integral around a circular contour, right? And in rectangular coordinates, that contour happened to be a square. And we'll recap that. So we need to get good at understanding how do we add up vector fields along some path in space. And I have prepared a slide for that yesterday for you guys, just to kind of get a good feeling for it, all right? So first thing here is we have, in order to understand that, we need to understand this vector derivative again. We presented this before, but I'm going to present it again because we're going to use it today. What is the derivative of a vector, right? Excuse me. In particular, a vector which is parameterizing a path. This vector, R, for example, has a parameter t. Oh, what was that? Okay. R here parameterizes this path, right? And as you increment the parameter t, you can think of it as time if you wish. As you increment that parameter t, this vector points to a different point. And each of those points, for each t, there's a new point, and it traces out a path, right? So first thing you need to know is the parameterization of the path. How do we find the derivative of that vector as a function of, or with respect to its parameter? Well, we can add a small displacement. As a matter of fact, it's even simpler than that. We just use the direct definition of a derivative from first semester calculus. dr dt is equal to the limit as delta t goes to 0, r of t plus delta t minus r of t over delta t, right? You've probably seen that as f of x plus h minus f of x over h, right? Limit as h goes to 0. So that's the exact definition. But how do we apply it to vectors? Well, we have r of t plus delta t. So that's this vector here, r of t plus delta t. And we subtract from it, using the ordinary laws of vector algebra, r of t. And if you do that subtraction, what you get is a vector which is head to tail rule, right? So you go from the tail to the head of, well, you have to flip one of them first because you're subtracting, and then tail to head. So you get this vector here. And as that parameter delta t goes to 0, those two vectors converge together, and you get what's called the tangent to the path, right? So whenever we integrate along a path, especially a parameterized path, we need the tangent vector because that tells us what direction to integrate it. So this is what we're going to use this vector derivative for. We need the tangent vector to the path. All right. So here, all right, so this comes from a website down here. These are not my animations. But what we have here is a parameterization of a path, a helix, all right? Up here, we have a helical path, which is parameterized by this function r of t, is a position vector. It points from the origin to each of those points on the helical path. You can parameterize it as cosine t of x, or cosine of t in the x direction, plus sine of t in the y direction, plus t over 3 pi in the z direction. So as time increases, say we don't have a z component, then we just have cosine of t and sine of t. That's just a circle, right? But as we parameterize the circle, we're lifting up in the z plane, in the z direction, by t over 3 pi. So this is going to trace out a helical path. The premise of the problem was that you have a small magnetized bead, that red bead, and we're going to slide it around the helical path. We're going to calculate the work done by a magnetic field, a constant magnetic field, which is generated by this green square. So that green square is a very strong magnet, and it generates a constant magnetic field in the x direction, minus x direction, in fact. All right. So we want to calculate the work done along this path. And to do that, we're going to have to integrate a vector field along some path, right? A path integral of a vector field. Okay. So what is the definition of the vector field F? Well, F is -1/2 x. So it's constant in the x direction, has a strength of -1/2 in that direction, right? So the idea is to calculate the work done. We already know ahead of time that the work done by the magnetic field on a charged particle is 0 because the force is always acting in right angles to the displacement, right? So it cannot change the kinetic energy of a charge, and therefore it can only change its direction. So acceleration can either be change of direction or change of kinetic energy, and or change of velocity. So it does no work. We know that ahead of time. But let's calculate it. The idea is to calculate the work done by the magnetic field as this magnetic bead is slid along the helical path. So how do we calculate work? It's F dot dl, right? So W is the work done is equal to the integration over this contour, or this path, of F, the force field, dotted with T ds, T hat ds, where T hat is the unit vector tangent to the path. And that's why we needed that vector derivative, right? So F dot dl along some particular path. Okay, well, if we now use the regular rules for integrating along paths, we evaluate this vector field at the points of the path, because that's what we're interested in calculating. We're interested in evaluating the force or dot product with the displacement at these points, right? The vector field at other points, like this arrow here, doesn't matter to us. Only thing we care about is the vector field F at the points in the path, right? So we need to evaluate this vector field F as a function of x, y, and z. We need to evaluate it at these points, R of t, obviously the path of the helix, right? So F evaluated at the points of interest for us, dotted with T hat, which is the unit vector. So we need DL, right? Basically, which is T hat, the unit vector as a function of T, and multiplied by the length of that vector. And that the length of that, the length of the derivative of the position vector, which is also the length of the tangent vector. This is you can think of this as a Jacobian. Okay, so what is R prime of T, right? So that's easy to calculate. Let's do that, yeah? So I didn't put that on the slide. So R prime of T is equal to, so we have to differentiate this vector R of T with respect to T. The first component, you do it component by component. The vector derivative, the derivative operator is distributive into these components, right? We differentiate each component. So the derivative of cosine is negative sine of T, excuse me, x hat. The derivative of sine is cosine in the y hat direction, and the derivative of T by 3 pi is 1 over 3 pi in the z direction, right? Now, we're going to take the dot product of, okay, so we can calculate the magnitude of this. Okay, so first thing we want to do is calculate this dot product, right? So F dotted with T hat. T hat is this divided by its own magnitude. So I think it's easier if we define it like this, right? T, the vector T is R, there should be T hat, sorry. T hat is equal to R prime of T divided by its magnitude or its length, right? The derivative divided by its length. We substitute that in for T hat here, and we cancel out these lengths, right? Okay, so now we have to take the dot product of F with R prime of T. And F only contains an x component, so we're going to pick up only this sine function here, and we're going to integrate from A to B. So from 0 to 6 pi, this 1/2 here comes out from the F. It's there. We have sine of T. There was a minus sign here and a minus sign here. They canceled. We have the integral of sine of T. Nothing could be easier. Minus 1/2 cosine of T from 0 to 6 pi. And we know that the cosine of T will give us a 0, right? So that's an example. The whole idea is this, in this picture. What you want to do is you need to have the tangent vector. The purple vector is the tangent vector to the path. And we're going to, we have that as a function of the parameterization of the path, just by differentiating the vector that describes the path, right? Then we take the dot product of each point at each parameter value with the vector field. We're adding up the vector field's contribution in the direction of the path. That's what the dot product is, right? That tangent vector, the purple vector, is in the direction of the path. I want to add up the contribution of that vector field in that direction at each point along the path. So the dot product gives me the component of a vector in the direction of another vector, right? For the vector which is taking the dot product with. So that's the idea. All right. So it's really good if you can kind of get your idea or your head around this idea, right? That to add up a vector field along some path, we take the dot product, the tangent to that path with the vector field all along the path. Good. So any questions?
So is it that period we would experience work on?
Yeah. I mean, these two, if you had chosen a different limit of integration, yes, that's true. So
It is experiencing work, but it's sort of regenerative, which the net result is zero work. But it is experiencing some work along the way.
okay, so it's a good observation. And what's happening here, I think, is normally a charged particle in a magnetic field that's constant experiences a force and right angles to the path of to the velocity vector of that charge. In this case, I think it's a little bit different. So we're kind of forcing this path. This is not the natural path of the charge. So it's a good observation, as a matter of fact. So please note that. So you can get some work out of this, but really it's not the classical sense of work being done by the magnetic field on the charge. It's a good point. Yes. Any other questions?
So could you explain again about the F vector, like how did it come minus 1 by 2 x cap?
Oh yeah, okay. So that was just provided, right? There's a large magnet. This green square is a large magnet and it produces a constant magnetic field. And the magnetic field here we're interpreting as the force field. And it's defined to be -1/2 x hat. It's always in the x hat direction. It's a constant vector field. And we define it to be -1/2 x. There's probably more physics behind it if we wanted to model the magnet and get a true magnetic field. But to this example was to illustrate how to calculate a path integral of some known vector field, right? Okay, great. Any other questions? Yes.
Remind me, what is ds, and then how do you get the t vector times the magnitude of r?
Very good. So ds here is arc length. When we differentiate, or sorry, when we integrate along a path, typically we integrate with respect to the arc length. So it's a length of arc, right? Normally, when you differentiate with respect to, or sorry, when you integrate with respect to x, you have dx, right? So it's some incremental distance along the x-axis, right? But in this case, we have some kind of path, a space curve in 3 dimensions. And in order to describe a differential displacement along that path, instead of saying dx or dy or dz, we say ds, which is a differential arc length along that path. Now, this comes from the direct definition of how to integrate a path integral in classical calculus, right? So what you do is you evaluate your vector or your function. Say this is a normal function. You evaluate it along the path, and ds you can write as the square root. Where can I write? So say it's 2 dimensions, right? So we have some path in here. What you can do is say, along this path, I can make a little triangle. So I'm gonna kind of blow up this little part of the path. And I can make a triangle like this. This is dx, this is dy. So this would be ds if it was small enough, right? Dx and dy. So then you can say ds is equal to the square root of dx squared plus dy squared, right? And what I can do next is I can factor out a dx. No, I want to divide through by dx, right? So same thing as factoring it out. Oh, why is it doing that? Okay, so factoring it out, right? So what you get here is a dx here, and you get the square root of 1 plus dy by dx squared. Yeah, does that work? Yeah, square root of dx squared, I bring that in, dx squared. Yeah, so this square root of 1 plus dy over dx squared is typically, related to the Jacobian, if you will, but we integrate with respect to dx instead. And this factor here is related to this factor here, right? This ds here is similar to r prime squared dt. It's another way to write it. Okay, hopefully that clarified a little. Mine may more confusing, but if you have more questions, let me know. Look it up, how to integrate along a path. And if it's still confusing, I can describe it a little bit more. Okay, any other questions? Good. All right. So now so we looked at Maxwell's equations, we looked at the units, we looked at how to do Taylor series expansion of vector fields, which we needed to define the divergence and the curl, right? So let me bring you back to here. Remember, when we did this, when we defined the curl, what did we do? We had by definition a path integral along a closed contour of the vector field dotted with dl. That's the same thing that we just looked at. It's a path integral, a closed path of a vector field along a circular path. In this case, it's a rectangular path, right? What am I doing then? I'm trying to take the dot product of a vector field A with a path that forms a circle. What am I calculating in the end then? I'm trying to define or trying to calculate whether this vector field A has non-zero net contribution along a circular path, right? By adding up the vector field dot product with the path, the L vector that goes in a circle. In the end, I'm calculating whether or not that vector field circulates along that path. If I do have a non-zero net contribution as I integrate that vector field A along this path in a circle, then that must mean that there was some amount of rotation of that vector field or circulation about this axis that points orthogonal to the plane of which I'm calculating this circulation integral. So that's why I wanted to bring that up. It should be more intuitive now what it means to calculate the curl of a vector field. From this definition, this integral is the circulation of that vector field around some path. Yeah? Cool. Okay, so we did all of that, right? We got to the gradient. So we define the gradient by kind of measuring a displacement or calculating the displacement of a scalar field, or the change in the scalar field rather, with respect to this displacement. So I have some point r, I want to change to r plus dr. I have a scalar field which I can evaluate. These don't have arrows, they're not bold. I can evaluate the scalar field at these 2 points, r and r plus dr. Or what I can say is, it's at this position and with respect to the displacement dr, what is the value of the scalar field at the new point? A differential displacement in some direction defined by dr, right? Okay, so what is the change in the scalar field along that path? Well, we know that it's the total derivative. We have to add up all the changes that are possible to the scalar field in each of these directions. So this is rise over run, this is a slope. I multiply it by a run, I get a rise. So I get the change in the vector, or change in the scalar field v in the x direction, multiplied by a displacement in the x direction, I get the change in the scalar field v, right? But it doesn't just change. So the total change in the scalar field v doesn't only depend on displacements in x, but also in y and also in z. I add them all up, total derivative. Okay, so that's the main premise behind it. Now all I have to do is recognize that I can write this change in the scalar field v in terms of a dot product of dr with some new vector, right? Some new quantity. This new vector is gradient to v, right? So if gradient to v, I can represent gradient to v like this, then, and dr we know, then this dot product is also the same change in the scalar function, right? Okay, so that tells us everything, because now we have a dot product and we know how to apply properties to dot products. If I have a dot product that results in 0, then what does that mean? The two vectors of the dot product of are orthogonal. So we now know that, excuse me, if I choose a displacement path that is orthogonal to this new thing I'm calling the gradient vector, then the function does not change value at all. Therefore, we can conclude that if I had, say this is a mountain in here, if I choose my dr displacement in this direction, and after that dr, I evaluate the change in the height of the mountain to 0, then I know I'm going orthogonal to whatever I'm calling this gradient vector to be. Or if I want to maximize a dot product, then dr must be in the same direction as where this other vector is, and we're calling it the gradient. So if I want the maximum change in the scalar field, then I should displace myself in the exact same direction as the gradient. All the properties of the gradient fall out of this. Very good. So the gradient operates, it's an operator. It operates on a scalar field and produces a vector field that tells you the greatest rate of increase of that function. So for example, here is this orange scalar field here, which is plotted as minus cosine squared of x plus cosine squared of y. And then we square all of that. So we have this kind of mountainous looking thing. And if I'm at the bottom here at the origin 0, 0, and I want to ascend in the greatest or in the fastest way I can, then I need to follow these gradients. These blue vectors are the gradients of this orange scalar field. And if I follow any of these vectors, I'm going up the fastest way I can, right? Great. Now remember, there is a blue vector associated with every point on this surface. So if I pick a point, then there is a way to go in the maximum rate of increase. Great. Any questions? Good. All right. So we need all these operators, right? Because we're talking about vector fields, and we need to evaluate how these vector fields change. And we're going to find that Maxwell's equations are written in the mathematical framework of vector calculus. So we got to get good at understanding this language so we can interpret Maxwell's equations and generate mental pictures, right? Like you read words out of a book, you convert that into pictures. You need to understand this language, which is what we're doing now, in order to convert equations to pictures. Otherwise, you just see symbols and you know how to operate on them arithmetically because you've learned the formulas to apply, but you don't see the physics as you do such a thing, right? So it's better to understand these definitions. Now we're going to talk about Laplacian, right? Laplacian measures what you would call the curvature of the field, and it tells you how much that the value of the field differs from its average value taken around the surrounding points of that field. And we'll understand that, right? So first way to understand this is the Laplacian operator. We write it as del squared operating on a scalar field. It operates on a scalar field. Can operate on a vector field. We'll see that later.
Sorry to interrupt.
No problem. Yes, please interrupt.
I'm unable to see if you're pointing or writing something.
I know it. The camera doesn't point to the screen. Well, I'll try to make my best efforts to use the iPad to point to things. I'll talk to them too and see if they can rotate that camera. It's much more effective pointing at the board. I'm sorry. I'll make sure I'll try to do that. Thank you for also everyone online. You can interrupt me and in the room. Just interrupt me. You don't even have to raise your hand. I don't take offense. I'd rather you understand what I'm saying and instead of me blow by the material and you get lost. Okay, so the first thing to understand here is that del squared f, Laplacian is an operator, del squared we represent it as, operates on the scalar field f, and you can define it as the divergence of the gradient. Okay, now remember what I said about divergence of a vector field. Previously, I said the divergence of a vector field picks out points of sources or sinks of a vector field, right? Let's go back and check that out real quick. Sources or sinks, yeah? When you take the divergence of a vector field, what you're finding is a new field, a scalar field. So I start with a vector field, I take the divergence, I operate on that vector field with this operator del dot, and it produces to me a new field, which is a scalar field. And that scalar field tells me the places of source or sink. If that scalar field has a 0 value, then all the flux went right through that point, right? No net flux through any box that I could put any differential volume around that point, as we saw last time. No, if I find a positive result, then that means that, remember here, if I find a positive result, then there must have been a source of flux that was inside of that box because net flux came out, but there wasn't a contribution that went in to cancel it. If I find a negative scalar value at that point, the divergent scalar field, then that means that source went in and it got terminated in that box. It was a sink because of the anti-parallel nature of the outward unit vector of the normal to the surface and the flux entering a box without having an exit ray, which cancels the contribution that entered. So divergence picks out points of sources or sinks of a vector field. Excuse me. So what does that mean for Laplacian? That means, okay. And then remember what we said about the gradient. The gradient is a vector field which points along the direction of maximum rate of increase, right? So you can kind of see it here already. This vector field in this plane looks like it has divergence, right? If I took the divergence of this gradient vector field, the blue field, then I would find that this minima of this scalar function has it's a source of that vector field, right? So you can kind of get it already, right? The divergence of a vector field, the gradient first off tells us the direction of maximum rate of increase. The divergence of that is going to pick out maximum minimum of this multivariate function, right? If it's a positive value, you're at a minimum. If it is a negative value, you're at a maximum. Okay, so that gives you some geometric intuition. Yes?
The gradient slide.
Yep.
Scalar field curve, and like, can you point out a couple points like that might have high or low and Gaussian values on that curve?
Yeah, definitely. So here we know that we have a high positive divergence, right? Because the vector field is diverging from that point. It's a minimum. If I'm at the very minimum of that scalar function, I'm standing in the bowl, no matter what direction I go, I'm going to go uphill, right? I'm at the minimum of the function. There's no other way no matter every way is up, right? That means the gradient is pointing up, it's pointing outward from me everywhere because I'm going uphill, right? Here, for example, let's see. So this has one minima and we're kind of picking out minima, but these, you might be able to find other minima at, or maxima rather, at these points, right? There might be some relation to maxima or minima. As a matter of fact, in here, it doesn't look like, so if I put a box here, remember what we said last time, if the vector field is growing with respect to, let's go back to that. If the vector field is growing, so yeah, it's true. If the same amount of flux goes in and exits, then it's all accounted for and it becomes zero. But if the vector field is increasing with rho, then that means that more flux is exiting than entering, right? So still there's a positive contribution. So here you might see that there's more flux entering than exiting. The vector field's getting weaker over here, right? So there you'll have some divergence there. You just gotta kind of calculate, go through. So the best thing you can do is develop the intuition, geometric intuition. There, everything's arithmetic, right? And we're very good at applying rules and doing arithmetic. So try to get the geometric intuition for this. This has one minima, so it has, it's most well-defined, or easiest to spot Laplacian is there. But this function has two. Yeah, here, look. This is the scalar field here, f. Here is its vector function gradient of f in the plane xy. And there is at this point, the vectors are all diverging. This is a source. And at this point, it's a sink. And these 2 points associate with these maximum minima. Yeah? Okay, so here's an easy to understand differential equation based on that. It's called the heat equation. Del squared U is partial U partial T. Right? So, excuse me, U can represent, let's say, the temperature. So the Laplacian, where we have a lot of curvature, right? Where the Laplacian is greatest is here, because the points all around it have more of an average value. They have a larger average value than this point. If I add up all the points in some circle, okay, so if I add up all the points along some circle here, they're greater than that value, right? So Laplacian is the average of all the neighboring points with respect to the central point. And that also means that if that happens, the curvature is greatest, right? Say I have a linear function, for example, and this is the point of interest. If I add up this point and this point, which are its neighboring points, for a linear function, I'm talking about 2 points only. The average of that goes to 0, right? This function has no curvature, it's linear. So that's how the Laplacian kind of picks out curvature. But if I had some kind of curved function like this, and I add up this point and this point, then I might have a non-zero contribution, the average with respect to the center point, right? Anyhow, this gives you the curvature. The more the curvature of the heat or the temperature, the faster that temperature is going to change, right? This should have a minus sign, I believe. The greater the curvature, the hotter this point is with respect to its neighboring points. If I take a source and I put a very hot source right here in space, then it's going to diffuse, right? And the hotter it is with respect to its neighboring points, the faster it diffuses. As soon as all the neighboring points are the same average temperature, no more diffusion. So that's what this picture is down here, right? We start with these hot spots and they kind of diffuse because the heat's spreading, right? Questions? All right. A lot of differential equations are written in these mathematical frameworks. So let's try to, we'll definitely unpack Maxwell's equations and understand them. So here's an example. A couple laws from electrostatics. We have the electric dipole moment of a dipole at the origin. Is this function here, V equals to P, which is the dipole moment, cosine of theta divided by 4 pi epsilon naught r squared. That's for a dipole at the origin. Okay, we know that the electric field is the gradient minus gradient of V. So V is the scalar field, the scalar potential field. The electric field is minus gradient of that. And we can calculate that gradient using this formula here. So we take this is in spherical coordinates. So we take, it only has an r and a theta component, or r and a theta dependence, right? So we get from it an r component only, and a theta component rather. I think there's a theta hat here missing. And we get this contribution here, right? So now, That's the gradient. This is the scalar field. We know that Maxwell's equation, divergence of D is equal to rho if it's a homogeneous space, and epsilon doesn't depend on position, because whenever we see these upside down triangles, anytime you see this upside down triangle, all you have to do is associate in your mind with some kind of spatial derivatives, right? Don't get scared. Just think of it as partial by partial x. It's a derivative with respect to space. We're just doing it in three dimensions now. So anytime I see partial by parts or upside down triangle, I just think of it as a spatial derivative. So I have this epsilon here. The only way I can factor something out of a derivative is if it doesn't depend on the variable which we're differentiating with respect to, which is space. So epsilon better be constant throughout space if I'm going to pull it out of that divergence operation. So then if I do that, I can divide. And then look what I have here, the divergence of the gradient, and that becomes the Laplacian. And what does this say? The sources and sinks of the potential function are at points of charge density. And we can see that over here. So this is kind of a plot of all of this. It's kind of busy. These spheres are scalar equipotentials, equipotential surfaces, and then the vector fields are the arrows. And here we can plot the potential, and what we see is the potential has maximum, minimum at the points of charge. So it's kind of a nice example that collects a lot of these operations. Questions on that? Very nice. Okay, so this should be a lot of review. Divergence theorem and Stokes theorem. So we need these two theorems because we use them a lot to convert from integral and differential form of Maxwell's equations. They're used in a lot of mathematical proofs involving involving Maxwell's equations and so forth. So we have two theorems, divergence theorem and Stokes theorem. You can think of these as reducing the dimensionality of an integration. Here I have a volume integral, which is becoming a surface integral by way of the divergence theorem. And I'm taking the volume integral of the divergence of A. Now remember, what did we do for the divergence? We took a small cubical volume and we calculated the dot product of the flux entering all six faces with the normal vector associated with that face, and we added them up, right? So you can see by nature of this construction, if I take a volume V and I break it down into a multiple of these little boxes, these cubes, and I calculate the divergence within each of those small cubes, and I add them up throughout the volume by the process of integration, then there's going to be a lot of cancellations. A flux line entering this box and going this way and exiting the volume exits with respect to this arrow here in the same direction, but it enters the neighboring box in the opposite, the normal vectors in the opposite direction. So any flux exiting the box, any flux exiting this box is going to give a contribution which exactly cancels this face, right? But exactly cancels this face of this box because of the normal vectors being in opposite direction. I can do that for all internal faces. So the only thing I have left are external faces. These faces here don't have a neighboring box with an oppositely pointing normal vector to cancel that contribution, right? So if everything in the volume cancels and all the only thing that's left is the flux on the surface, then I can rewrite this integral over the volume of the divergence of A as the surface integral of the flux dotted with ds, the surface flux integral, right? A dotted with ds, where ds is a differential vector, differential surface area vector along this surface, the outer surface of that. Yeah. Okay, hopefully that makes pictorial sense at least, right?
So can you explain that?
What's that?
How the formula derived?
Yeah, so you can think of it here. When I calculate the divergence of A, right, at a given point, say I do it for this box, what do? I calculate A dotted with the closed surface integral. So you remember A, right? The divergence of A is equal to the limit as delta S goes to 0 of the closed surface integral of A dotted with ds divided by delta dv, dv, right? This closed surface integral here splits into 1, 2, 3, 4, 5, 6 faces, right? I have to account for the flux over all 6 faces. So I calculate the flux A dotted with ds for each of these faces. Say I start with this face here. The normal vector is in that direction. I calculate A dotted with ds. if that is 0, then the flux didn't exit that face at all. It was orthogonal to that face. If A dotted with ds is maximized, then the flux is exiting that box normally, right? Maximally. Now, okay, so I calculate divergence of A for that cube. But now I'm saying I'm going to add up by integration over the volume. I'm going to add up the divergence for all points in that volume, or for all boxes in that volume that I could draw. Remember, these boxes are supposed to be infinitesimal, associated with a point. We take the limit. That's what this limit means. The limit as that box shrinks to a point. I add that up for all the points. So now I'm going to calculate the divergence for this box. And when I do that, the normal vector for that box is that way. So whatever contribution that I got from this face of that box is going to exactly cancel when it enters into the neighboring box. And that's true for all internal faces in the volume. What I can't say is when I calculate the divergence of that face there, there's no box that that neighbors it and cancels it, right? So now that face is also the boundary of V or S. And this normal, the normal to that face, oh my gosh. Okay, the normal to that box is the normal to the surface S at that point, right? So now it's just A dotted with ds, where ds is now the surface vector, the surface unit normal, and ds over the surface, right? Okay, good. All right, let's do Stokes' theorem. I know we got to get through this stuff. It's going to get super fun when we get to materials and we get to wave equation. We're going to start feeling very empowered, like we're really learning a lot. So here, we got to get through this language. We all got to speak the same language. So let's get through this, yeah? Stokes' theorem is the next one. We have, so what we're going to do here is convert a surface integral into a path integral. So this is for an open surface now. If we have an open surface, say S like this, there's a contour L which goes around the surface. And I want to calculate the curl of the vector field A with respect to that surface, right? So here's the normal vector. We calculate the curl for that normal vector, right? That circulation of the vector field around the path, which is orthogonal to that normal vector, right? That's this path here. We do the same thing. A dotted with DL around that path. Add it up. Okay. Now, it's the same argument. I have a path integral this way, that way, that way, that way for that particular point. I have a neighboring path. So this one has a path which goes up that way, down, and to the right. The neighboring path has, remember, they're always right-handed paths. This path here, one path goes that way, and the neighboring path goes that way. So you cancel internal edges now. And the only thing left is the edge around the contour of the whole surface. So I convert the curl of A, integrating and adding it up over the whole surface, into A dotted with DL, which is the remaining paths that weren't canceled in the interior of the volume, right? Say this path here. That path doesn't have a neighboring box over here to cancel it. So I still have to calculate A dot DL with that. And that's true for all of these exterior DLs, right? Okay, so let's do some examples with them. Gauss's law in integral form is, we're going to derive it from Gauss's law in differential form. Divergence of D equals rho. All right, what do? Take the volume integral of both sides of this equation, right? Whatever I do to one side, I do to the other, and I can do whatever I want to either side of the equation. It still maintains the equality. That's the whole point of this mathematical construct, is one side, equality between two quantities. If I take the integral of both sides, I still maintain the equality, the equation is still valid. Okay, now use divergence theorem to convert the volume integral of the divergence of D into the surface integral of D dotted with ds. And we know what the volume integral of rho dV is, because rho is the charge density with respect to, or with units of coulombs per meter cubed. If I integrate over a volume, then I'm going to get coulombs in the end. All the charge inside of that volume, Q enclosed. Let's do one with Stokes. The curl of H is J plus partial D partial T. Take the surface integral of both sides, right? It still has the same equality. On the left, I'm taking the surface integral of the curl of H dotted with ds. I can write that as H dot dl, which is integrating H around the circular path bounding the surface S, right? if I integrate j dotted with ds, now that vector j is sort of penetrating the surface ds, then I get the total current enclosed. And then this integral I can't do anything with yet. The last one. I can factor out partial by partial t. Yeah. You probably have done this before, hopefully. Okay, great. So let's look at the gradient theorem. All right, so this is a fun picture, so we're gonna understand it. First, given a multivariate function phi of x, y, and z, and three single value variable functions rather. Here, we have a multivariate function. We have three single variable functions, x, y, and z, yeah? Comprising the vector r. So these are the scalar functions which parameterize a path r of t. We can use a multivariate chain rule, and we can derive a consequence. It's called the gradient theorem. We're going to derive it. Okay, so I think first let's understand this picture. So here, this picture in the lower right, what do we have? We have some color plot, right? That color plot is phi. It's a scalar field of x, y, and z, and you assign to each of these points some scalar value, right? Okay. The next thing is the black arrows are the gradient of that scalar field. The gradient says I point in the direction maximum rate of increase, right? So which is maximum, blue or red? Red, right? So the scalar field or the vector field, the gradient of phi points in the direction of maximum rate of increase of that scalar field value. Here, the maximum rate is away from this point because the minimum. So going back to your question, the Laplacian of this black vector field is a scalar field which it has a negative value here and a positive value here, right? Or sorry, positive here, negative here. It's opposite. Okay, good. Now, that's the scalar field and the vector field. The next thing is I have an XYZ coordinate system in which all of these fields are defined in. I have some path, this path, white path, which is gamma. That white path gamma is parameterized by the vector r of t, right? So let me see if I can do this. Yeah, r of t is here. We have this, the endpoint r of a, where t is equal to a, and the other endpoint of the path r of b, where t is equal to b. We have this path, this white path gamma, all right? What do I want to do? I want to add up the vector field gradient of phi along that path gamma. So it's similar to what we were talking about at the beginning with the helix, right? I want to add up the contributions of the gradient of phi along this path. How do I do that? I take the dot product of the vector at each point, the vector field, with the tangent vector of the path, right? So that's what's going on here. How do we find the tangent vector to the path? You guys know how to do that, right? Here's the tangent vector. Differentiate this r of t. And it gives us the tangent vector. So let's do it. So the integration of the gradient of phi over some path r of t parameterizing the path gamma, where gamma goes from a to b, is independent of the path gamma. That's what we're going to prove here. So we're going to integrate the gradient of phi dotted with dr. From the definition of a line integral, again, we evaluate our function that we're integrating over the path at the points of the path, because that's the only points we care about. We're taking the dot product with r prime of t along that path dt, right? All right, so we can rewrite that using the multivariate chain rule here as this function here becomes d by dt phi of r of t using the multivariate chain rule. So I apply the chain rule okay, so this is phi as a function of r of t, right? And I want to differentiate it with respect to t. So if I want to differentiate with respect to t, then I have to use the chain rule because it's a composite function, and therefore partial phi, partial x, and then dx dt. But of course, that's a multivariate function, so I have to do that for all three of the variable dependencies. And if you analyze, so, okay, does everyone understand from here to here? Forget about this other part. Forget about the second equality. The first equality, does it make sense? Yeah, good. All right. Now all I have to do is look at that thing and say, oh, I can write that as the gradient of phi dot with r of t as a dot product. So once you recognize that, then you can you can go to this equality. I can make this into that. And then I can use the second fundamental theorem of calculus. It says that the derivative of a function with respect, the derivative of the integral of a function is just the evaluation of these endpoints. Okay. Gradient theorem. What does that mean if it only depends on the endpoints? It means that the value of the integral of the gradient over some path gamma is independent of the path. It means it only depends on the endpoints. I could choose any path, I get the same result. And thus we conclude that the gradient of phi is a scalar, or sorry, it's a conservative vector field. We already know that, right? And we can also then say that the curl of the gradient of phi is equal to 0. There's no curl. Okay, good. Questions? All right, so you're getting crash course, right, on this stuff. All right, so here's another theorem. We gotta get through these theorems, yeah, but we're gonna use them in the course. Green's integral theorem. I have a volume V bounded by a surface S, has an outward normal n hat. And what do I want to say here? I want to state these two integral identities first. So we have the integral of f dotted with ds over the surface, right? I have some vector field f, and I want to add up the integral, the flux of that vector field f through the surface, ds, yeah? So ds is n hat, ds is ds n hat, right? So for every little differential surface area here, I have a unit vector there. I might have the vector field f exiting the surface like that. I want to take the dot product of all such points. So here's another point. Here's an n hat with a ds, and the vector field here maybe that way. And then here's another n hat with a ds, and the vector field maybe that way, right? So I want to take the dot product of f dotted with ds, add it up over the whole surface. I'm finding the flux that's leaving, or that's penetrating that surface. Net flux could be going in, could be going out. What is the net value? Well, by the divergence theorem, that is the volume integral of divergence of f dv in reverse, right? Okay. Now what I'm going to do is I'm going to let f. So, okay, when you first see these things, like, who thought of this? Where did they get inspiration? Why did all of a sudden I say f? I'm going to define as f gradient of g. And for that, you just have to see these things enough times, know the result you're trying to get to. So they must have already had some idea of what they were after. And they thought, well, if I make this substitution, I get to where I'm going, where I know I'm already going. So it's kind of a pull out of thin air, f equal to f gradient of g, but we'll see why. So f equal to f gradient of g. There's a vector. Oh my goodness. There's a vector field. We have f on this side. It's a vector field. So we better have a vector field on this side. Gradient of g is a vector field. Plug that in here. All right. Now what we do is we use the divergence theorem again. So divergence of now this f gradient of g. All right. Then we have this vector identity we can apply to the integrand, and we can rewrite it like this. This is called Green's first integral identity. All right. Right now it has no value, right? You don't understand what we could do with it. It's hard to make a geometric interpretation of it even, but it's a mathematical identity that we're going to keep in our pocket for now, all right? We'll see the power of it later. If you interchange f and g, subtract, then you can create another equality, right? All we have to do is maintain equality. If I have two equations, I can multiply 1 by 10 and 1 by 5 and subtract the 2, and I still maintain equality. And I'm making all these different identities or useful equalities that might be useful later, all right? So that's Green's second integral identity. Just know that you've seen them, and if you never need to use them, or when we use them, we can come back to this slide, okay? Here's one place where we're going to use it. Vector field uniqueness. So I have the volume V. I have a vector field F. You'll see in a minute why I can say that I have uniquely defined this vector field by specifying its curl and divergence. Why didn't I just write F in that volume? I could, but I could also write the curl and the divergence of F, and that also uniquely specifies F, right? And we'll see how that becomes useful. Given the divergence and curl of a well-behaved vector function F in volume V and its normal component F dotted with Dn on surface S, prove that F is unique, right? What are we saying? If we specify the divergence and the curl of a vector field and its normal component throughout some surface that bounds volume V, we can prove that we've uniquely defined F. So, okay, that might be, why are we doing that? Well, later on, you're going to see that Maxwell's equations, there are two vector fields, E and H, right? And there are four Maxwell's equations. Why are there four? Because we need to define the divergence and the curl of both E and F to uniquely specify E and F. So we need those four equations. That's why there are four. Based on this theorem, right? We have to have the divergence and the curl specified in order to uniquely specify vector field E, and the divergence of H, curl of H to specify H uniquely. So let's prove it. Suppose F is not unique by contradiction. Then another vector field G would satisfy the same conditions, all right? So that means within V, the divergence of F is also the divergence of G, where G and F are not the same, aka F is not unique. And the curl of F is equal to the curl of G. And on the surface S, we have F dotted with N is also equal to G dotted with N. Okay, so let H, a third vector field, equal to the difference between these two vector fields, right? Why are we doing that? Because we want to prove that H is zero, meaning that, or we want to prove that, we want to prove that H is not zero, really. No, H is zero. So F is equal to G. So there is no such other vector field G that's different than F. If I try to specify a G, the only thing that's the math will tell me is that G is the same as F, because there's only one vector field. So if H is zero, then that means we've proven that F and G are the same, or F is unique if we specify the curl and the divergence of F. H is equal to F minus G. Okay, what is the divergence of H then? Well, the divergence of H has to be zero because, here, look, the divergence of F is the divergence of G. So the divergence of H, which is equal to the divergence of F minus G, well, that equals to the divergence of F minus the divergence of G. And since those are exactly the same vector fields, by our assumption, that's equal to zero. Okay, the curl of H is zero by a similar argument. And we can say that H, we can define, because the curl of H is zero. We know that the curl of the gradient of any vector or any scalar field is equal to zero, right? We just proved that in the last slide by the gradient integral theorem, right? The curl of the gradient of any vector field, scalar field, is equal to zero. Yeah. Okay. Okay. By the last slide. So then we can say, well, then we can call H the gradient of phi because the curl of H is zero. So let's call it the gradient of phi. We do that a lot. We're going to do that later in the course too. Okay. So H dotted with N. H is now the gradient of phi. So that's the gradient of phi dotted with N. And we can say that N hat is ds, right? So the gradient of phi ds is equal to zero. Okay. Hence, the gradient of phi is orthogonal to ds because these two dot products, this is a dot product. So the gradient of phi is orthogonal to ds. Okay, so finally we have two more things to understand, then we can prove it. The divergence of H is the divergence of the gradient of phi because we said H is the gradient of phi. And therefore, this is the Laplacian of phi from 2 slides ago. And we know that the divergence of H is already zero, so the Laplacian of phi is equal to zero. All right, we're almost there. Use Green's first integral identity. Let's go back. This one. Use Green's first integral identity with f equal to phi conjugate and g equal to phi. All right, so here, the integral identity is that the surface integral of f gradient of g dot of ds is equal to this volume integral. All right, so the surface integral of f, which is phi conjugate, and g, the gradient of g, where g is phi, is this, right? Well, that's equal to the volume integral of the same quantities by that Green's first integral identity. All right, so it's like a place where this weird equation that we derived is useful, right? Otherwise, I haven't seen it used in any other place. Maybe in moment method formulations. So I take that back. There is a place where they use it in moment method formulations, but it proves useful to prove vector field uniqueness, which is a super useful result. Okay, so zero. Why is the left-hand side zero? What? Lost your voice again? My gosh. Last semester, same thing. So what do we know about gradient of phi and ds? Yes, gradient of phi is orthogonal to ds. One thing we derived based on the construction of the problem. So left side is 0, yeah? Okay. The right side, if you work all this out, you get the gradient of phi conjugate dotted with the gradient of phi. And we know from arithmetic rules of complex numbers that, you know, a conjugate dotted with a is the magnitude of a squared. So the magnitude of h squared dv is equal to 0. And because the volume integral of some function is equal to 0, the argument is equal to 0. So h has to be 0, which means f is equal to g, which means f is unique, which means that if I specify the curl and the divergence of a vector field, and of course the normal component on the surface, then, and we'll see even that normal component is not necessary. We'll make an argument for that. Then I've specified f uniquely. So now, okay, so let me go back. Let me go forward. I think I show, oh no, what's that? That's unfortunate. Okay. Let me see if I can use the other one. Some of the fonts got messed up. Here. Now you know why there are 4 Maxwell equations, right? What are these 4 Maxwell equations? We just said that if we specify the curl and the divergence of a vector field, we uniquely specify it. We need both. You can't specify one. And if we want unique solutions to this differential equation, if we solve Maxwell's equations, if we get an E and an H, if we want to be sure that we solved the problem and we got the exact answer, the only answer, the answer, then we better have a unique answer. So these two first laws are specifying the divergence and the curl of the vector field E once you introduce the constitutive relations, right? And these 2 Maxwell equations are specifying the divergence and the curl of H. We need all 4. Yeah, that's why there are 4. Okay, good. All right. So there's some flow to this. Okay, here's a related thing. Now we're going to get rid of that need for the normal component specification because Maxwell equations are 4 differential equations that we specify, but we don't ever say that we also need the normal components with them, right? So how can we get rid of that? Okay, on the last slide, we just proved that the vector field is uniquely specified by giving its divergence and curl within a simply connected region and its normal component on the boundary. Now we're going to say if the field vanishes at least as fast as 1 over r, as r approaches to infinity, which is true for radiation, which is true for which is true for the vector fields E and H that we're going to consider, right? Then only its divergence and curl need to be specified. We don't need to specify the normal components as well. So, and we'll see exactly why that happens, right? Because what we can do is we can say, we'll take the surface off to infinity. That's what this S going to infinity means, right? And if you do that, if you make the surface go off to infinity, then the normal component of the vector field dies off fast. It reaches 1 over r as r goes to infinity. So when r becomes infinity, that vector field is 0 on that surface, through that surface at infinity. So that field f dot with ds is 0 anyway, right? So we then just need the curl of f and the divergence of f. Okay, so we can say that curl is divergence is an irrotational component of the vector field, and the curl is solenoidal. It's showing a decomposition, right? If I want to take some function and I want to express it in terms of a new basis, then I might have, you know, Taylor series basis or something. I can decompose. That's why it's called a decomposition theorem. I can decompose a vector field f into these 2 components, right? These 2 mutually exclusive components. Why are they mutually exclusive? Because the curl of f is equal to 0. The curl of f is rotational is 0, but its divergence is non-zero. So it's the irrotational part of the vector field. And then I have the other side, which is the opposite. The curl is not 0, but the divergence is. So it's a nice clean decomposition into 2 mutually exclusive things. And so we can also show by this identity that I pulled out earlier, curl of negative gradient of phi is equal to 0, that we can say that the F irrotational is equal to negative gradient of phi, because the curl is equal to 0 of the irrotational part. Therefore, I can say that F irrotational is gradient of phi. That's one thing. Over here, I use a different vector identity. The divergence of the curl of any vector field is 0. And that vector field is the solenoidal. So the curl of A could be the solenoidal, right? Some vector field A. If you put these two together, you get a vector field which is defined in terms of its potentials. We're going to see this later in the course. Okay, good. All right. So now you know why there are 4 Maxwell's equations, except something happened to the slide. Hopefully it's right in your notes. I'll fix it in the canvas if it's not. All right. Same slide as I showed you just a minute ago, but I added this these 2 statements to it. All right. Excuse me. Summary of vector calculus operations. We're almost done with all of that, right? We're getting something really cool next, which is the generalized coordinates. So we have this table kind of summarizes it all. Gradient, divergence, curl, Laplacian, and the curl of the curl, which we need for the vector Laplacian. So here we have the symbol, we have the objects of which it operates on, and the result of the operation. So the first one is the gradient. It operates on a scalar field and produces a vector field. The divergence operates on a vector field and produces a scalar field. The curl operates on a vector field, produces a vector field. Laplacian operates on a scalar field and generates another scalar field. The Laplacian of a vector now, if it operates on a vector field, it produces another vector field. We're going to use that later. And the curl of the curl operates on a vector field, gives you another vector field. And here's the definitions in Cartesian coordinates. I don't want you to memorize these. If you're going to memorize one thing, I want you to memorize these definitions in what we're going to learn next, which is generalized coordinates. Then you've learned them in every coordinate system, and you can apply them directly. Okay, here's all the formulas for 3 major coordinate systems taken from Wikipedia: Cartesian, cylindrical, and spherical. You have all these little definitions. When you're doing your homework problems, you can come back to these notes and look at this slide in case you need these formulas. Here's some identities, which you'll use throughout your studies of electromagnetic theory. These are ones involving differentiation. These upside down triangles are nothing but spatial derivatives, x, y, and z. And then we have some involving vectors alone. Okay. Oh yeah, so let's look at this. Okay. All right, so you might have not noticed yet, but all the vector fields that we've been writing in this course have script lettering. Script means like this fancy letter, yeah? H, E, and all that. We're gonna get rid of those after this slide and the next. We're gonna use regular letters, and you'll see why. So what are we showing here first off? A vector field, consider the vector field H, which is 2 components, x and z. And those components, so I evaluate this function at x, y, z, and t, and I say that's the value, whatever, that's going to become a scalar number. A scalar number, a real number, hx. I evaluate this at some given point, x, y, z, and a value at a point in time t. And I evaluate this function, I get some scalar number, that's my x component. I do the same thing with hz, and I get the z component. I add those 2 together, and I get the vector field H. The problem is this vector field is a function of x, y, z, and t. And t could be arbitrary. It could be a pulse, a square wave pulse. It could be a triangle sawtooth function. It could be, Heaviside step. It could be anything, right? We're going to specialize in this course to what's called sinusoidal or time harmonic variation. We're going to assume that the time dependence is always cosinusoidal for all vector fields. Why is that a good assumption? Why didn't I choose square wave? Why didn't I choose steps or whatever, right? Maybe one of you guys can figure it out. What do you think? What's cool about sinusoids? Yeah. What's that? Differentiable, right? Yeah. Yeah, that's a good thing.
They're like continuous and they're like bounded, so that they'll just oscillate.
That's also true. Yeah, low in the interaction here. Yes.
You use sinusoidal to define your functions?
Yeah.
Because any function that you have, you can separate it to many frequencies of sinusoidal.
Correct. Yes. If by Fourier series and Fourier theorems, Fourier transforms, I can synthesize any temporal dependence of a vector field by summing up its sinusoidal contributions, right? Different frequencies. So it's a natural decomposition. If I can solve Maxwell's equations for, okay, say the time dependence of this is some square wave. If you gave me even a square wave, I would be dead in the water. I wouldn't know what to do. Of course, I know what to do, but if, saying that I didn't know what to do, it's a square wave. What I would do is I would solve Maxwell's equations for sinusoidal functions, cosine of omega t, cosine 2 omega t, or whatever. And then I would add up all those components to synthesize the triangular or the square wave dependence of time. So what we're going to do is reduce all that complexity of temporal dependence to solving Maxwell's equations for sinusoidal time dependence, which is called time harmonics. That is going to also provide some really useful benefits that we're going to see where we just eliminate time altogether. And we're now solving Maxwell's equations for x, y, and z only. So let's see how that works. Here's the TE10 waveguide. We'll learn about waveguides later, actually next semester. Waveguides. We'll see them here and there in this semester though. We're gonna do a lot more interesting things than waveguides this semester. Okay, first off, here is the sinusoidal dependence of this vector field. So, all right, so let's stare at this for a second. We have a wave here, right? Obviously we have, this is the H field right here that you're looking at in green and blue at the top of the slide, this thing here. This is the H field, the H, script H, right? So at every given spot, say here, that's some x naught, y naught, z naught, right? And it varies as a function of time, right? There's a vector there, and as time increases, that vector is changing. So what you can think about here is, let's look at this vector field right there. Let me erase that. I want to try to concentrate on that green vector. What is it doing? It's not moving left or right. It's not changing position. It's just going up and down, right? Sinusoidally. All right. Imagine you're at the baseball stadium. I don't know if you guys have been to the baseball stadium. Every person in their seat goes up and then sits back down, and it's called the wave. It goes around the stadium, right? No person moves left or right. They just move up and down, but you see the wave effect going around the stadium. That's exactly what's happening here. Each one of these vectors are going up and down by themselves. They don't even know about their neighbors. They're just going up and down in some synchronous way. And that's creating what's the effect of a wave. Yeah, the wave is traveling down the waveguide. All right, here's a cross-sectional view of that. And what we can see here is the blue vectors of the magnetic field, the green vectors of the electric field of the TE10 waveguide mode, which we'll learn about later. Now, these blue vectors, let's concentrate on one of these. How about this one right here? What does it look like it's doing? Rotating, right? How can it be rotating? Let's look at this here. Here we have H decomposed into an HX and an HY. Should be HX, HZ. Sorry, HX, HZ. Excuse me. HX, HZ. If these two vectors, so HX, look at the red arrow. All it does is oscillate sinusoidally up and down, right? Person in the seat at a baseball stadium. The blue vector also does the same thing, up and down by itself, without even knowledge of the red arrow. But they are out of phase by 90 degrees. This leads to what's called circular polarization. We'll see that later. And that's exactly what happens to electric field vectors. They rotate in a circle like that. So if you add H is equal to the superposition of HX and HZ, right? If I add those two vectors, I get the blue vector, which is rotating in a circle. Just because one person's going up and down in their seat, 90 degrees out of phase with the other person, right? So the vector starts to circulate. Okay. So what if we knew that each of these vectors are varying sinusoidally, and all of them had the same sinusoidal temporal dependence? What I can effectively do is factor out that temporal dependence and leave these vectors fixed in space as sort of a time snapshot. So I freeze time. All these vectors will be pointing in different directions. but I factor out the temporal dependence because they all have the same temporal dependence. I solve for that snapshot in time, or if you want to think of it that way. And then at the end, I multiply back the temporal dependence to all of those and let them oscillate. And that's what we're going to do. So sinusoidal temporal variation invokes the concept of phase and amplitude, of course. So yeah, okay, now that we're talking about sinusoids, we're talking about their amplitude, their phase, and so forth, right? If you had some square wave or something, what is the phase of a square wave? Okay, you could probably define the phase of a square wave if it's periodic. But some random temporal function, right? Some squiggly line in time has no meaning for phase. But now we're talking about sinusoids. We have phase and amplitude and frequency. Okay, here is this sort of temporal snapshot. All those vectors are defined like that. They're a function of x, y, and z only now, not time. I can solve for these using a new form of Maxwell equations we're going to derive. Solve for this picture. Then I can turn on time, flip a light switch. Each of these oscillate sinusoidally, right? Each of those vectors now have cosine of omega t multiplied onto them. And then the whole dynamic picture goes back to this. So let's see how do we do that. Okay, we have Maxwell's equations. E with the script has temporal dependence. That's equal to Ex in general, Ey plus Ez, right? Now, if I assume that Ex, Y, and Z can be written as some spatial dependence, some function that tells you what that vector field is in terms of spatial coordinates, and I can say explicitly define now not just any time dependence, but cosine of omega t plus phi. So you give me an x, y, z in some point in space. I give you the vector, the x component of the vector here, field here, and then I also tell you that that vector is going to vary cosinusoidally. So if I give you this vector, then it starts to go like this, right? All right. So I explicitly define a particular type of temporal dependence. All right, let's see what happens. So I take the curl of E minus partial B partial T, Maxwell's equations. So because this, remember, these curl upside down triangle is spatial derivatives only, the temporal function can come out, right? So cosine of omega t comes out of the derivative because this is a derivative with respect to space. And then over here, I have a temporal derivative. I have to differentiate cosine. I get sine, and then I get this, right? Of course, I'm missing the omega. So somebody, we got to add that, yeah? Okay. So problem here is I still have a Maxwell equation. This is still Maxwell's equations, right? It's still Maxwell equation, but it has temporal dependence still. What can I do to get rid of temporal dependence? Let's say instead of cosine, then I say E now as a function of x, y, z, and t. The script E has temporal dependence. The straight E does not, Ex, x, y, and z. But now I say E to the j omega t plus phi. All right. If it's E to the j omega t, so I'm still specifying a particular type of temporal dependence. And in fact, it's the same. It's sinusoidal, right? But okay, what's the benefit of that? So now we have Ex of x, y, z, and t plus E to the j phi. So there are a couple of, okay, so we're going to get rid of the time dependence, but we're going to pay the price. But it'll be better. E to the j omega t. Curl of E minus partial B partial t. We can still factor out the temporal dependence here. We have E of x, y, z. Then we can differentiate the temporal dependence here. Differentiate this. We get j omega E to the j omega t. Now we can cancel the E to the j omega t's. And look what's left. A Maxwell equation which has no time dependence. This is way easier to solve, maybe. Depending on what temporal dependence you specify, right? This is now a Maxwell equation that we're going to use. What is the price we paid? I've already written it down, but it would be cool if you guys had saw it. What is the price we paid to get rid of time? We now have to solve this Maxwell equation in the complex number domain, right? Now, this is all real numbers. These vector field measurements in nature are real valued functions. They're real numbers, right? But this new domain where I got rid of time is sort of this domain which models reality, models nature, but it's not directly measurable in nature. So when we solve this Maxwell equation and we get B and E, we always have to go back to the real domain, to the temporal domain, by multiplying by E to j omega t, and we're going to see that take the real part of that. We'll see that. But anyway, this is easier to solve. But now we have complex numbers, J, and we have E now. This vector E is a complex number, complex valued vector field, complex valued vector function. So vector fields are now complex valued, but it's going to make it a lot easier. We'll see. What time is it? Okay. So last slide. We start with time-dependent Maxwell equations, divergence of D, all these have script letters, all of these. So, and then the vector field E has these three components. These are real valued functions. We can solve them directly and we get the electric field, right? That's the actual electric field. This is the only thing that is in reality. But now, if we instead use this other domain, I have all straight letters here, right? I can solve these. These are functions of space only, E, X, Y, Z, X, Y, Z, X, Y, Z, not time. I solve for this, but these are complex valued functions, right? They're complex valued functions. I solve for E of X, Y, and Z, and then I need to go back to the real domain by using this construct here, which is the actual vector field is equal to the real part of the vector field I solved through these Maxwell equations multiplied by E to the G omega Z. Yeah. A lot of times we stop here anyway, right? When we solve the problem, we stop here because we know we can do this. And we can always, this is more of a dynamic picture, right? We just, once we have this, we have solved the problem. Any questions? Yes.
On the previous slide, you lose the phasor permission.
No. So now that they're complex valued, this vector here is a different phase than this one, right? It's shorter, you know, there's a phase relationship between all of these vectors, right? This, if they, so this one starts at a different phase than this one, for example. So you solve for that phase offset. Then you add time and they all oscillate. It's exactly a snapshot of this, right? If I take a snapshot, then I just factor out, I turn off the time, right? Time variation. I get this picture. Now, by turning back on time, I just multiply each of those vectors by E to J omega T and take the real part. Okay. You'll see. We'll work with this more. Yes?
So could you give an example of the cases when we need the time-dependent equation and when we don't?
Okay, in engineering, you're going to use the time independent all the time, right? You can always get to the time dependent from the time independent. These are much easier to solve. If you need to solve time dependent directly, then maybe one example is when you solve for dynamics, an algorithm called finite difference time domain. You can solve Maxwell's equations in the time domain, and you can watch like pulses, Gaussian pulses reflecting off of surfaces. We'll see a lot of those animations in this course. Or if there's some, okay, so it's kind of hard to solve a differential equation for an arbitrary function. We'll see that even for current distributions that are arbitrary. But if a temporal dependence is arbitrary, it's easier to solve it for one frequency or a given frequency in general, omega, and add up the results if you want to synthesize temporal dependence in general. Yeah. Any other questions? Good. All right, great. I'll see you guys on Tuesday. Yes.
I'm an exchange student from France, and I have some courses to take. And I need to understand. I have the first course because I need to change some courses. I have to them. What is the aim of this course? Because it seems like talking with my professors back in France, some of them I already. It may be similar to what I already have.
Okay.
So
yeah, what we're gonna do is, if you want like a big overview of the course, I've added a lot of extra topics from like research and things that are expanded upon beyond the book. But the book for the course is Advanced Engineering Electromagnetics from Balanis. We're gonna study that whole book in this course and the next. So it's an Advanced Engineering Electromagnetics book. And if you look at the table of contents, we're gonna learn all of that. but half of it in this course, half of it in the follow-on course next semester.
Okay.
And but I've added a lot of extra stuff that's not in that book. They're like advanced techniques to solve problems and such.
So the aim is like to solve the theoretical problems of electromagnetic waves propagation.
It's all the classical theory of electromagnetics and the advanced topics and such. There's some applications maybe sprinkled throughout, but it's mostly on the theory, the advanced theory of electromagnetism.
All right, because I think I've had the application, but like not the theory in depth.
Yeah.
So maybe it adds value. So
It'll be cool. I mean, I always love to see, Maxwell equations or explanations of the theory from different perspectives, even if I've seen it before.
Yeah.
It helps me learn it better, from another person's perspective, they understand it in a different way.
Yeah.